Okay, we're looking at question 74 of chapter 10. It says a uniform 0.03 kilogram rod of length 0.4 meters rotates in a horizontal plane about a fixed axis through its center and perpendicular to the rod. Two small rings, each with a mass of 0.02 kilograms, are mounted so that they can slide along the rod. They are initially held by catches at positions 0.05 meters on each side of the center of the rod, and the system is rotating at 48.0 revolutions a minute with no other changes in the system. The catches are released and the rings slide outward along the rod and fly off at the ends. What is the angular speed of the system at the instant when the rings reach the end of the rod? B, after the rod leaves, what are the speed of the rings as they leave it? And so, so the law of conservation is going to say that the angular velocity, they're going to be equal to each other. So the angular velocity multiplied by the inertia is going to be equal to the angular velocity multiplied by the inertia of the part 1. And so if we rewrite this in terms of angular velocity sub 2 is going to be equal to the angular velocity sub 1 multiplied by the inertia sub 1 divided by inertia sub 2. And so the way we find the inertia is this equation right here. So it's going to be 1/12 times the mass times the length squared plus 2 times the mass times the radius squared. And so you can see down here, so we have 48 revolutions a minute, which is going to be our initial angular velocity multiplied by multiplied by this right here. And so this is going to be the inertia 1/2. And so it's going to be 1/12 times 0.03 times 0.4 squared plus 2 times 0.02 times 0.05 divided by 1/12 times 0.03 times 0.4 squared plus 2 times 0.02 times 0.4 squared, which is going to be 12 revolutions a minute. And so that's how fast it's going to be when it gets to the very end. And then it's not, once it leaves, it's going to still have the same common angular velocity, so it would remain the same at 12. So it would remain the same.